Okay, let us take one more problem to understand the unsymmetrical case. So here the problem given as a tie member of truss consists of ISA 65 by 65 by 6 mm of Fe410 grade is welded to an 8 gusset plate. Design a weld to transmit to the full strength of member. Assume shop welding. So here, typical one truss member joint is been given. This is a truss member. As you know, the truss will be like this. This is the truss, and it consists of various members like this. So in this case, uh, one typical joint is been given, a single member joint. So let us assume this is the one joint having a gusset plate. For the gusset plate, these members are coming and joining, and let us assume this enlarged view of the joint is this one. Okay, so here one tie member is been connecting to the gusset plate, and this is the gusset plate. This one is the gusset plate, and for this gusset plate, this is the tie member, tension member, that is a angle section. This angle section that is 65 by 65 by 6 mm is connected, and here the question asked here is design the weld to transfer the full strength of the member. Means the load, how much to be transferred is not been given, so that load to be calculating by using a codal provision. So this full strength of the load, let us take it as a TDZ, design tensile strength of gross member, that is to be calculating. Since the load how much to be transferred is not been given, we have to calculate by using this formula. And once we get how much load to be transferred, and for this load what is the length of weld required on these two sides, since it's an unsymmetrical case, the length we get are of different. So because the load is not same on either side, so obviously we get L1 and L2 lengths, those two lengths to be calculating, and also the TDG to be calculating. So this is the problem given here. Um, so the solution here, uh, here first, uh, from the IS handbook or a steel table, we need to take the properties of ISA 65 by 65 by 6 mm from the steel table. So just you refer the steel table. So you will be getting, if you're referring the steel table, you will get the properties of the section. So you will get all the properties of the sections. So in this problem, we are having a section 65 by 65 by 6 mm. So this is the 60, this one. This is 65 by 65 by 6 mm, this one. So for this we need to take the properties here. Here for 65 by 65 6, so we need to take what is the uh, area, and as well as CXX and EXX. So here marked CXX and EXX, this one CXX and EXX, that is the centroid or centroid of the section. So these two things to be taken here, that is CXX and EXX, this one here, this is CXX and this is EXX, and these to be taken from the steel table, as well as area to be taken. Area is taken here, and CXX centroid where the load is being acting, that is to be taken and marked in a section here. Then the tensile capacity of the member to be calculated. So this is the tensile capacity of the member. So this formula you get from the code TDZ AZ into Fy divided by gamma MO, where gamma MO is the partial safety factor for the material 1.1, Fy is the yield stress of the material at 250, and after substituting these all values in the above equation, we get the tensile capacity of the member, that is 169.1 kilonewton. So once we get the uh, strength of the member, that is TDZ, next for this load, that is 169.1 kilonewton, we get here 169.1 kilonewton. For this load, what is the length of the weld required? Oh, we need to calculate here. So before calculating the length of the weld, first we need to calculate the how much thickness of weld to be provided. So the thickness of weld, it depends upon the edge conditions, as I discussed earlier. So the thickness of weld is depend upon the edge condition. If the round edge is present, the thickness will be given in the code book. If the square edge also, the thicknesses are given in the code book. Refer code book and apply the same thickness for the section here. Since, so in this case, the size of the weld not exceed 3/4 of T at the round edges. So round edges means, so here we get the round edges, here we get the round edges, and here we get the square edges. So for both we need to calculate the thickness, then comparing both the minimum thickness to be providing. Okay, so here the size of the weld 3/4 of T, that is 4.5 mm, that is the maximum thickness, and maximum size of weld. First we need to calculate the minimum thickness for the given section. Table number 21 we need to refer. Then for the maximum size of the weld, for the round edges, this is the thickness, and also for the square edges, this is the thickness. Hence provide the size of the weld as 4 mm. So from first we have to calculate minimum, then we have to calculate maximum. The minimum thickness is based on the thickness of the plate. Up to 10 mm thickness, the minimum size of the weld to be providing is 3 mm. Then maximum size of the weld, as I discussed, for the round edge, and for the square edge. Then these two thicknesses are given for the round edge and for the square edge. The minimum is 3, maximum need to provide 4.5 mm. In between we need to provide, hence size of the weld becomes 4 mm. Then the thickness of weld, becomes that the effective throat thickness 0.7 times of S. This one 0.7 times of S. Since it's a fillet weld, the shape of the weld is a triangular shape, and the effective throat thickness will be this one, effective throat thickness T, and this T is given as K into S, where K is the angle of fillet weld. So generally 45 degree to be taken. For 45 degree, 0.7 into the size of the weld, it becomes 2.8 mm. So once we get the thickness of the weld, then we need to calculate the design strength of weld per millimeter run. The design strength of weld per millimeter run, as you know how to calculate per millimeter run, that is this one, per millimeter run, that is area into stress in the weld. Area is the length into thickness of the weld. The length to be taken as 1 millimeter run, then the thickness already we have calculated, then this will be the stress in the weld, Fu divided by root of 3 gamma mw. So where Fu is the 410, gamma mw is 1.25 for the shop welding, and if suppose if it is a welding in a site, this gamma mw to be taken 1.5. Then the Lw is the effective length of the weld. Here effective length of the weld to be considering is 1 mm. Then after substituting these all values in the above equation, we get the unit strength of weld, that is strength of weld for 1 millimeter run. So since we don't know the length of the weld, here you may take even length, you may keep the length of the weld as it is, that is Lw, or else you can take the 1 mm for the 1 mm weld, what is the strength, and after getting that strength, you can substitute in the equation. Here what is been done, the equating the tensile capacity of the member to the design strength of the weld. Whatever the tensile capacity of the strength you have been obtained, you have to equate to the above equations. You will get the length of the weld here. That is, they are equated this one, and you have got length of the weld. Then L1 and L2 are the length of top and bottom weld as shown in the figure. So here it is shown here in this figure, L1 and L2 are the top and bottom length of the weld for the applied load, L1 and L2. Then CG of the angle section is at a distance of 18.1 mm from the top, that is CXX. So this to be taken from the steel table. So this 18.11, it will be from here top to at the center, CG. That is, CG of the angle section is at a distance of 18.1 mm from the top, that is CXX. To make a center of gravity of weld to coincide with that of angle, then here we have to apply the Varignon's theorem. The Varignon's theorem to be applied here. So how they are obtained here? L1. So this side is L1 and this side is L2. It is given here. I'll show you. L1 and L2 here. This is L1 and this is L2. Then we have to take the moment about any one end. Then here taken L1 into 18.1 is equal to L2 65 minus 18.1. Then you will be getting L1 2.59 L2. Then LW equal to L1 plus L2. Then LW is, you know already, 318.91. Then substitute here L1. Then you will be getting a L2 length. Then again you will be getting the L1 length. Then provide L2 and L1. Okay. So this is the procedure how to calculate L1 and L2 length for the unsymmetrical case. So whatever the length you obtained, finally you have to apply or you have to mark at this point and this point here, L1 and L2. So this is for the unsymmetrical case, and that to single angle connected to the gusset plate.